Let's just quickly take a look at the partial fraction section. Again, this is something that you probably should have seen in your pre-calculus class. How do you do partial fractions? Of course, not in the context of finding antiderivatives, but just doing them on their own. So maybe just a quick review of that, and I'm going to use this first example as a motivator for that because we're going to have to do the partial fraction decomposition anyway. Might as well use this for our review of that topic. So if we remember partial fraction decomposition, if you haven't seen it before, I mean, that's possible. I think in some of our pre-cal sections, maybe the instructor skipped it or something. If you haven't seen it before, it's not that big of a deal. We can just pick it up now. The idea is that we want to start with a fraction like this and decompose it into two other fractions, fractional expressions anyway. In order to do that, we have to factor this thing. And this is the difference of squares. So step one is to always just factor it. And then what we do from here is realize that now I have two factors in the denominator here. I know that my new decomposed expression is going to have two fractions in it. One of them is going to be over one of those factors, and the other one is going to be over the other factor. And the thing about partial fractions, we don't know what that a and the b are going to be. We don't know what they are. So we have to do this whole technique to figure out what it's going to be. What is the a and the b? And if you think about what's going on here, just sort of as an aside here, if I give you something like this, you see that, I hope everybody in the class could do that without thinking too much about it. This is just, finding a common denominator, right? X plus 3, x plus 1 is the LCD, so we'd have to multiply, numerator and denominator by what we need to get that LCD. Right, so something like this. And then we could add them. This is going to give us x plus 3 plus 2x plus 2 over the common denominator, x plus 3, x plus 1. Right, this is something that you would have probably learned in intermediate algebra, in fact. And you would have gotten 3x plus 5 at the end of this. And then if you multiply that out, you get x squared plus 4x plus 3, I guess. Right, so this is the intermediate algebra way of doing this, right? Going in that direction. Adding two fractional expressions that don't have the same denominator, right? Finding the LCD, adding them, etc. What we're doing now is we're going backwards in the other direction. I would like to figure out how do I get from this term to the one that I started with, these two things added together, right? And, right away, it's probably like, how do you tell if you started with a 3x and a 5 here, how do you know that it's going to end up as a 1 and a 2 like that, right? Hence here, how do I know what these are going to be, the a and the b here, right? Everybody going to see the procedure here? So that's the idea. We want to be able to start out with something that is already combined and then separate it into its two, as they call it, partial fraction pieces of the original fraction. So that's what we're doing here. Now, how do I figure out what the a and the b are going to be? How do I do that? So the way to do it is we're just going to focus on this part of the equation, just that piece right there. What do I do with that piece? I multiply through by the LCD, and this thing in the denominator here is the LCD right here. That is the LCD. So what I'm going to do is multiply the entire equation through by that. 2x minus 1, 2x plus 1. Okay, and I have to do that on both sides. So 2x minus 1, 2x plus 1. Now, of course, on the left side, that's just going to have the effect of canceling everything out, and all we're going to be left with on the left side is just a 1. On the right side, when I distribute that to both of these, you see that in the first case, that is going to cancel that, right? And so I'll be left with just a 2x plus 1, so a times 2x plus 1. And then on the other one, when I distribute it to here, you see that the x plus 1 terms are going to cancel, but I'll still have that one left, right? And so there, on the other term, I'm going to have a b times the 2x minus 1. Okay, now the first way of doing this is what's called equating coefficients. This way works pretty well. In fact, it works every time if you want to do it this way. There's another method as well that I'll show you in a second here, but this just means you distribute everything. So you're going to get 2ax plus a plus 2bx minus b. And then you just put all of the terms that have an x together. You get 2a plus 2bx plus a minus b. Okay, everybody see what I did? I just combined the terms that have an x, factor the x out, and then I combine the terms that don't have an x and put those together. Now, equating coefficients just means I have a polynomial on the left and I have a polynomial on the right. Anytime I have two polynomials equal to each other, only way that can happen is if the constant terms equal the constant terms and the first power x terms equal the first power x terms. So basically what I have on the left is a constant term, 1, and then I have a constant term a minus b on the right. That tells me that a minus b has to equal 1. And then this is a term that has an x. Well, there's no x term over here, right? This could be considered 0x plus 1. So the x term here has to equal the x term here. And so I'm going to get another equation, 2a plus 2b is equal to 0. Now, if I take that first equation and multiply it by 2, I'm going to get 2a minus 2b is equal to 2. I'm just taking this and multiplying it by 2, and then putting it right there. And then I have a system of equations that I can do elimination on. So that tells me that a is equal to 1/2. And if I know what a is, then I can plug it into that first equation, 1/2 plus b is equal to 1. So b looks like it's also 1/2. So that should be minus b, sorry. Minus b. So that means that b, in that case, is negative 1/2. So now that I've identified both a and b, we're almost done here. I know we're in our last minute here, but we're almost done. So that tells us that now that I know what a and b are, I can come back up here and say my new integral is going to be this, because I did the partial fraction decomposition. We found that a was 1/2 over this 2x minus 1, and then the other one was negative 1/2. So 2x plus 1, and so that's our integral that we can solve now. Now that can be done by just regular old substitution. You could write that as 1/2 integral dx over 2x minus 1, and then have another integral 1/2 integral dx over 2x plus 1. Now for those, you could say u is equal to, for example, the first one, 2x minus 1. Du is then 2 dx. And divide both sides by 2 and get that. And so this integral is going to become 1/4 integral just du over u. And by a very similar substitution, this is going to become 1/4 du over u as well, although the u would be different here. This is different. In fact, I would probably call that dw over w. And you could say for this one that w was equal to 2x plus 1, etc. Same exact thing there. And then you could say the final answer here is 1/4 natural log of u, but what was u? U was 2x minus 1. The next one, 1/2, sorry, 1/4 ln w was 2x plus 1 in that case. So there we go. All right, so we saw that first example of how these work. Let's do a couple more. So we've also seen that one example that we did, the thing that we were trying to do the partial fraction decomposition for, had only two linear terms. So let's see what happens when we don't have linear terms, but we have quadratic terms when we factor it. You can kind of see that quadratic factors make you have to do something differently on the partial fraction decomposition. And when you have a quadratic factor, it's a irreducible quadratic. That's the idea there. Okay, so this looks kind of like a mess. Quadratic divided by a cubic looks like a pretty difficult integral. The way that we want to start all of these, if the denominator is not factored already, we have to factor it. In fact, I think that says the, no, that's not the first step. Oh yeah, it's the second step, factor the denominator. So, and then notice that step one on this, it says you have to divide if it's an improper rational function. Remember what improper means in the context of rational functions. It means that the degrees are either equal or the degree of the numerator is greater than the degree of the denominator. That's what improper means. And if it is improper, then you have to do long division or synthetic division, probably long division on it actually too. So this is a cubic. We got to factor a cubic polynomial here. Remember how we're supposed to do that. Factoring a cubic, hopefully it's factorable by grouping. If it's not factorable by grouping, then you do have other options, but it gets a little bit complicated. In this case, we actually can factor it by grouping, so let's just do that. Remember, for factoring by grouping, you look at the first two terms and factor out what you can just from those two, and then check the other two terms. Maybe you have to factor something out of those. In this case, you don't. But notice that when you do that, you get the x plus 2. That's the key for factoring by grouping, is that when you do factor out of the first two terms, that whatever is in those parentheses there is the same thing. That's what has to happen. And then after you do that, you can then factor out that x minus 2, since it's common to both. If you do that, then you're left with x squared plus 1 in this situation. So that means what we're trying to do from here is find the partial fraction decomposition for this expression here. Okay, then for that, one of those factors in the denominator is an irreducible quadratic factor. And if you check on step 4 there, what do you do when you have quadratic factors in the denominator? Irreducible just means you can't factor it anymore in the real number system. X squared plus 1 certainly can't be factored in the real numbers. So what do we do? Well, if it's a linear factor, then it just gets a single letter over that linear factor, as we saw in that previous example. If it's a quadratic factor, then you have to have two unknowns in the numerator. One of them has to have an x with it. So basically you have a linear factor in the numerator. And that means that we actually have to solve for three unknowns in this case. Everybody clear on what you have to do when you have an irreducible quadratic factor in the denominator? You have to have two letters on the top, something x plus something else. Okay. We also haven't seen what do you do when you have repeated linear factors. We'll do one of those in a bit as well. And then the worst ones that you have are repeated irreducible quadratic factors. That would be like if this term in the denominator here, if that were squared, that would be a repeated quadratic factor. Those ones get to be kind of messy. We actually have one of those to do. All right, anyway, so now we need to figure out what the A, the B, and the C are. So we just do the same thing that we did before, and then multiply through by the LCD. So in this case, the LCD is that. So we're going to multiply the left side by that. We're going to multiply the right side by that also. Okay, and then when we do that on the left, everything cancels, and we're just left with what's in the numerator. That's exactly what we want to have happen. On the right side, we're going to be distributing all of that to there, and then also all of that to there. When you distribute it to the first term, a over x minus 2, the x minus 2 terms are going to cancel, and we're going to still be left with the x squared plus 1 term. So we'll have on this side a times x squared plus 1 And then when you distribute it to the second term, the x squared plus 1 terms cancel, and you're left with the x minus 2 term. That's what we get. Okay, so last time I showed you one method of dealing with or trying to figure out what these constants are, and that is to equate coefficients. That means we'd have to expand out that right side and put it in order of decreasing power, collect all the terms that have x squared, all the terms that have x, etc. There's another way to do it as well, and that is to pick a particular value for x. Because what we actually have here in this equation, what is this equation really saying here? It's saying that we have a polynomial, right? A second degree polynomial with three coefficients, right? 5, 3, and 1. And we're setting it equal to another polynomial over here. All of this is also a polynomial, okay? And when you have one polynomial that is equal to another polynomial, that equality has to remain true for any value of x. Okay, so that means that we are able to pick any value of x that we want to here, plug it in, and then that should help us to figure out what the a, b, and c are. And there's a couple of values of x that are, well, probably a lot better than others. We can kind of see over here. What would be a good choice to plug in here for x? You look at that term there. What would be a good choice? Let's let x be something. That something in this case, to help us out here, maybe cancel some stuff out. First choice, I think, is 2. You let x equal 2, what happens? Well, you have to do that on both sides. So if I plug in 2 here in the first term there, I get 2 squared is 4 times 5 is 20, and then minus 6. 20 minus 6 is 14 plus 1 is 15. So I get 15 on the left side. If I plug in 2 on the second term, I get 2 squared is 4 plus 1 is 5, so I get 5a there. Now notice that when I plug in 2 there, that makes all of that 0. And then since it's multiplied by this also, that is also going to be 0. All of that's going to become 0. That's why 2 was a really good choice here. And you can see all we have left now is just the a, the unknown a. So we can easily find that a. A is equal to 3. Everybody see how that worked? And then what's another good choice for x? Because we have to find 3 unknowns here. So what would be another good choice for x? Well, again, looking at the right side, what would make something disappear if I let x be that something? Well, right there, you see, if I let x be 0, then that's going to take care of that b term right there, right? And that's going to just disappear. So 0 is another good choice for x. In fact, 0 is usually probably the best second choice, sometimes even the best first choice for what to let x be. So if x is 0, then on the left side, I'm just going to have a 1. And on the right side, I'm going to have just a there, 0 squared plus 1, which is an a. And then 0 here makes the b term go away, but that c term is still going to be there. 0 here gives me a minus 2. I'm going to have minus 2c. Okay. So the b term is gone. All I have left is a and c, but I know what a is already, right? So that makes it easy, because if a is 3, if I plug in 3 here, and then I subtract it from both sides, now I have a minus 2 over there, so minus 2 to minus 2c, so that tells me that c is 1. Okay, now sometimes you can't pick x to be, something that's going to make one of those letters disappear. Like we just saw that if we let x be 2, then that whole last term just goes away, including both the b and the c, right? Then when we let x be 0, the b went away. Well, there's no other choices here for x, unfortunately, that's going to make any of those variables disappear, but we already know what 2 of them are. So that's helpful, and now our last choice can really be anything, but you can maybe make it a bit of a smarter choice than others. I'm looking at this term right here and thinking, if I let x be 3, then this whole thing just becomes 1, and 1 times anything is better than, something else times that thing. So let's go with 3 for our last choice for x. Again, that it really doesn't matter. I mean, you could really just pick any three x values you wanted to, and that would create three different equations. But you'd probably want to be strategic about it. Okay, so if I plug in 3 for the left side, here I'm going to get 9 times 5 is 45 minus 9. So that's 36 plus 1 is 37, I think. And if I plug in 3 on the right side, I get 3 squared plus 1, that's 10a. And then if I plug in 3 for the rest of it, I get plus 3b plus c. Again, to see what I'm doing here, I'm plugging in 3 right there. That gets me to 3b plus c. 3 right there makes that 1, right? So it's 1 times b plus bx plus. Right. All right, now, again, the only thing that we have left to do is find what b is. So let's go ahead and plug in what the other ones are. We now know what a and c are, right? So if I plug in 3 for a, that's going to be 30 right there, plus 3b, and then minus, or sorry, plus 1. And so that's 31 on the right side. And if I subtract 31 from both sides, I get 6, right? So 6 is equal to 3b. And then we can solve for b by division, get that b is equal to 2. Okay, so this is a second alternative method of figuring out what those um, coefficients are going to be. Picking various values for x. You basically need to pick as many values for x as there are equation or unknowns, I mean, so that you can create one equation for every unknown. Okay. So here we had 3 unknowns, we needed to pick 3 values for x. If we had 4 unknowns, we'd have to pick 4 values for x. And it's even possible to like combine these two methods, the one that we saw yesterday and the one that we're seeing right now. Like if you run out of options for x, you could go ahead and do that equating coefficients technique and then just know what, one or two of the variables already is. One or two of the a, b, and c, or whatever they are. All right, so now with all that, we now know what a, b, and c are. So our integral that we're trying to find, we can rewrite it as, what was a? A was 3, so 3 over x minus 2 plus b was 2, so we have 2x, and c is 1, so 2x plus 1 over x squared plus 1. Okay, everybody see what we did with the partial fraction decomposition? We now have the same integral, but it looks different, and we can probably do this a bit easier than we could the other one. So that first one, in fact, is pretty straightforward. The first one is just 3 ln x minus 2. Second one, in fact, I'm just going to split this up. This first one here, easy. 3 natural log x minus 2. The other two, we actually have to split that up into 2 integrals. That right there, we can write as integral 2x, we'll split it up over x squared plus 1, and then plus, in fact, I'm going to do that as a separate integral, plus another integral, 1 over x squared plus 1. Okay, everybody see what we're doing there? So we basically have 3 integrals that we have to find. The first one was not too bad. This second one here, we can do it by substitution. We can say that u is equal to x squared 1. Du is then 2x dx. Well, that's nice because that's exactly what's already here, 2x dx, right? So there's a 2x dx. We know that's just going to turn into du in our new integral. And so that integral is going to become du over u. And as we know, just like the other one, du over u integral is ln u. And then that can further be written as ln x squared plus 1. And I'm dropping the absolute value bars there because x squared plus 1 is never negative, so we don't really need them there. And then finally, the last one, anybody recognize that one? What was the integral for that thing there? That one we actually don't even have to do any work on if you recognize the integral. Let's see what that is. We should be recognizing that one. That was actually talked about at the end of Calculus 1. So everybody should be recognizing that as an arctan integral. That's what it is. Yeah, inverse tangent. Yep. So this is equal to inverse tangent of x. So putting all these together, final answer here is 3 ln x minus 2 plus ln x squared plus 1 plus arctan, or inverse tangent, I should say, since I wrote that before. Inverse tangent of x. And then the plus c. Yeah, so if we're not remembering that arctan integral, I can just show you a nice formula for that very important integral. Get this memorized. You don't already have it. The integral of du over this, not the square root, over u squared plus a squared is equal to 1 over a, inverse tangent or arctangent of u over a. So definitely know that integral. That is super important. We're going to see that a lot of that here. I just want to point out we didn't actually get an example like this. You are going to get one in problem 1 that I'll have you work on. But when you have a repeated linear factor, what I'm saying, let me just kind of show you what you, I'm not going to do an entire integral like this, but I'll just show you kind of how you would approach the partial fraction decomposition. Suppose that you had something like this, I don't know, 2 over x squared minus 2x plus 1. Just notice that that factors to be x minus 1 squared, right? And so what that is, that's a repeated linear factor. We have x minus 1, and then it's squared. And if you look at what to do in that case, it says, step 3, for each factor of the form px plus q to the power of m, the partial fraction decomposition must include the following sum of m fractions. So notice that if we have an m power on the denominator, that means we're going to have that many terms on the right side. So I have a second power on the denominator. That means I'm going to have 2 terms on the other side. And the way that you decide what those are, you just basically list all the possible powers up to m. So in this case, it's x minus 1 and x minus 1 squared. So you have an a there and a b there. Okay, so basically you have an unknown variable for every power that is. So if that was a third power, for example, I would have to put a plus c over x minus 1 to the third. The fourth power, I'd have to also put a plus d over x minus 1 to the fourth. Okay, so that's how you deal with the repeated linear factors. And then the procedure after that works exactly the same way as what we've already done. So right now I'm just going to show you example 3, which is a pretty difficult one, because if you notice what it has there, repeated quadratic factors. And that works the same way as repeated linear factors, except you have to put what you would put for a regular, for just the first power of a quadratic. That means you got to have 2 of them, 1 for each power of the quadratic. This is already factored, so we can actually skip step 1 here. And I'm going to go ahead and just do the partial fraction decomposition first. Okay, so, and then also just verify that this is not improper. If you were to go ahead and expand that denominator, you would have a 4th power in the denominator. That's not improper because the denominator has the larger power. Remember, improper means same power or numerator greater power. Okay, so repeated quadratic, how do you deal with those? Well, you have to have an ax plus b for the first power of this quadratic. And then you have to have a cx plus d, 2 more variables, for the second power of the quadratic. Everybody kind of see how that works? That's repeated quadratic factors. Kind of similar to what we said for repeated linear factors, except for quadratics, you got to have both. You have to have the ax plus b or something x plus something in the numerator for each one of those factors. So basically, for a quadratic factor, there's two unknowns for each power of that quadratic factor. And so if I were to have maybe that denominator started out as a third power, well, then we'd have to have an ex plus f over x squared plus 1 to the third power, right? So just it gets to be a real mess because, introducing two variables for each power, that makes the problem that much more difficult as you go through. Anyway, the next step is the same as we have done for all the other ones. Multiply through by the LCD. Stop me if you have any questions here. I know this is probably not that easy right now, especially if you've never seen partial fraction decompositions before. Okay, so again, multiply both sides by the LCD. That cancels that denominator. And then this gets distributed to both again. So if you distribute it to the first term, notice it's x squared plus 1 squared, but there's only one of them in the denominator. So that means only one of them cancels. One of them doesn't cancel. So that means we're still going to have an x squared plus 1 there. And the second term, they both cancel, right? It's x squared plus 1 squared. That's the same thing in the denominator there. So this one does cancel the denominator. You're just left with that. Cx plus d. Okay, now part of that other technique that we saw, the one about picking values for x, if you pick certain values for x, there's really only one value of x that's going to serve us much of a purpose here, and that's x equals 0. So let's just go ahead and do that. I told you that we could combine these methods, so I'm in fact going to do that in this case. If we let x equals 0, that will allow us to at least find that one equation. I let x equals 0. On the left side, I would get 0. On the right side, I would get just b plus d. Everybody see that? I'm plugging in 0 for x here. That makes the a go away. Plug in 0 there. For that x, I get just 1 times the b there. So that's just b. And then if I plug in 0 there, that c term goes away, and I just have d left. So this tells me this is something useful. At least it doesn't solve for any of the variables right away, but it does tell us something about the way the variables are related to each other. It tells us that b is equal to negative d, right? So that's kind of useful. That means if we find one of them, we'll know that the other one is just the negative of it. So just for practice on the other method, now that we already know that b equals negative d, let's go ahead and try that other method just for practice again. The other method was to, this one, if I'm remembering correctly, we could actually pick a couple more values for x, b. It would work pretty well. But again, just for practice, what we're going to do again is expand all this, boil that out. So if I do that, I get ax to the third, and then my second power term is bx squared, and my first power term is ax. And my constant term is just b. And then the rest of it is just the same as it was. Okay, now remember the goal here is to equate coefficients, meaning that we would like to put all the powers together in descending order of power on the right side here. So there's only one cubic, there's only one quadratic, which is nice. There are two first power terms, right? The ax and the cx, so we can write that as a plus cx. And then there's also two constant terms. We can put those together as b plus d. Then, if you remember how this works, what we have on the left side and what we have on the right side are both third-degree polynomials. In order for two polynomials to be equal to each other, their coefficients all have to be equal to each other. So this works out pretty nicely because you can see that's all that's with the x cubed term. And what's the coefficient there? It's just 1, right? And so that tells us that a equals 1. And then the second one, the second power terms, there's the second power term there. There's the second power term there. Again, there's only one. That's it. There's no like b plus c or something like that. So that makes that easy as well. I can just immediately say that b is equal to 2. The first power terms, there's actually an a plus c there. First power term there, there's a 2 coefficient, so that means a plus c has to equal 2. And then the last one, in fact, we've already done that last one. We'll get the same result here. Notice there is no constant term on the right side, or sorry, on the left side, right? There's no constant term there. But that means there is 0 there. We could write that as plus 0 on the end. So that tells us, again, what we already knew. B plus D is equal to 0. Or B is equal to negative D. All right, well, that's pretty much enough because now I know what A is, and this third equation, A plus C equals 2. If A is equal to 1, then I can just subtract 1 from both sides and get that C is also equal to 1. Then this one here, since I know what that B is 2, I know that D must be negative 2. Okay, so now I've got all the unknowns, all 4 of them. This one was actually turned out to be not bad as far as the partial fraction decomposition. Some of these can get kind of nasty because, like I say, in this case, it worked out pretty nicely that we had just a single letter right here, right? Not like a plus 2c or 3, maybe sometimes even 3 letters right there. And also here, we had just a single letter by the x squared term. Again, that doesn't always happen. You could have up to 3 letters there, maybe even 4. And if that's the case, if you have like complicated coefficients on all of those, then what's going to end up happening is you're going to get 4 different equations, all with a, b, c, and d in them, right? So you have like a plus b plus 2c plus 3d equals something, and then 4 equations just like that. How do you solve a system of 4 equations with 4 unknowns? Yeah, it's not easy. In fact, it takes some linear algebra to do that. If you guys have taken or seen anything like that, reducing a matrix is what is required there when these get kind of complicated. Row reduction on a matrix. Anyway, we're still not done with this problem. We've just found the partial fraction decomposition, so let's go ahead and write the integral in its new form. The new integral will look like same integral, just a different form. Ax plus b. A was 1, so x plus b was 2, so x plus 2 over x squared plus 1 plus cx plus d. Well, c was 1, so x, and then d was minus 2, so x minus 2 there, over x squared plus 1 squared. And so the point of partial fraction decomposition is that hopefully your new integrals are going to be somewhat easier, or at least doable, something that you can actually do. That's the whole idea here. We want to be able to do these integrals. And so what's going to happen in this case, the only way to really approach these is to split this up into 4 different integrals. Just like we did on that last problem, we had to split it up into 2 different integrals. This one we have 4. And then we have to determine how easy is it to do these 4 integrals. We have techniques to do all of them. Let's hope so. Okay, so there they are, 4 integrals that we have to do now. Now let's just go through and make sure that we have techniques to do all of these 4 integrals. And I'm just going to say, what is the technique here? Integral number 1. How would we do that one? What's the technique we need for that one? U sub, exactly. U sub, u equals x squared plus 1 du 2x dx. We don't have a 2 there, we just have an x dx, so we'll divide both sides by 2. We'll get 1/2 du is x dx. And then the integral becomes 1/2 integral du over u, which, as we know, becomes 1/2 ln, and then in this case x squared plus 1. We don't need the absolute value again because it's positive inside the parentheses. Okay, then the second one. Integral number 2. How do we do that? Actually, that one would not be a substitution. That would be similar to the one we did on the last problem. There's no x up in the numerator. So remember, I just said a very important integral. This one actually doesn't even require any work. It's just 2 arctan. Okay, the third one. Integral number 3. How do we do that? So now would actually be a good time to say the same as the first one, u sub. This is also u sub. Here we would say that u is equal to the same thing, in fact, x squared plus 1, and then du is 2x dx. Again, there's not a 2x, there's a x dx, so we'll divide both sides by 2. And then the integral becomes 1/2 du. Now in this case, it's over u squared, right? But in that case, we'd have to write that as 1/2 integral u to the minus 2 power. And then we can use the power rule on that one to get negative 1/2 u to the negative 1, which is the same as negative 1 over 2 u. And then that is the same as negative 1 over 2, what was u, x squared plus 1. Okay. Any questions so far? Getting this? So 3 of them were really not that bad. Just regular u substitutions for 2 of them. The other one was just, didn't even really have to do anything on number 2. Now, number 4, though, what are we going to do with this one? What is the technique on that one? Anybody have an idea? So that one, actually, we just learned that technique for number 4. The only way to do that one, unfortunately, is by trig sub. So you can kind of see that integration by partial fractions, it can be somewhat easy, like that first problem we did, but it can also be pretty difficult. Like in this problem, we had to do the partial fraction decomposition. That produced 4 different integrals, and then one of those actually requires integration by trig substitution, which itself is a pretty difficult process. So now this one has to be done by trig sub. So it's actually not that bad of a trig sub, so let's just quickly do that. And this one we're going to say x is equal to, do you remember what the substitution is here? What it should be according to the form that we see? Yeah, a is 1, and so you're talking about the first form. It's the one that has the x squared plus a squared, right? And that's the tangent substitution. So x has to be equal to the tangent of theta. And so then what happens to x squared plus 1 squared? X squared plus 1 squared becomes tan squared theta plus 1 squared. But tan squared plus 1 is secant squared, right? So that's just secant squared or secant to the 4th. And then we also, I guess, we need to do dx as well. Dx is equal to the derivative of tangent is secant squared. And so with all that, the integral is going to become 2 dx. So let's see, 2 dx was secant squared. And then the denominator we said became secant to the 4th. The second power, well, actually, all of that will cancel, and that will become a second power. And so what we're left with basically there is 2 over secant squared. But that's probably better written, rather than having the secant in the denominator, we could write that as having a cosine in the numerator. And then we have to deal with the cosine squared integral. Well, for that one, again, remember what the deal with that is. power reducing identity. So 1/2 plus 1/2 cosine 2 theta. Notice that the 2 and the 1/2s there will cancel each other out. So we're going to get, so the 2's are going to cancel each other out. So we're just going to get the integral of 1 plus cosine 2 theta there. Okay, then the antiderivative of that, theta plus 1/2 sine 2 theta. And if you remember, in order to deal with that sine 2 theta, to change it back into x's, we can't have a 2 theta there, so we have to use a double angle identity there. Just the identities all over the place there. And if you remember the identity, yeah, we still also have to draw the triangle, but we are going to have to deal with that sine 2 theta. So let's deal with that at the same time. Remember the identity for sine 2 theta, it's 2 sine theta cosine theta, and then at least the 1/2 and the 2 cancel there. Then, so what do we have here? We have theta plus 1/2. Oh, sorry, no 1/2 anymore. Theta plus sine theta cosine theta. And then we draw our triangle. And what do we know about the theta? We said that x was equal to tan theta. So if x is tan theta, then that means we could put an x here and a 1 here, right? Opposite, we can write that as x over 1. So opposite is x, adjacent is 1. Hypotenuse is the square root of the sum of the squares of these two, so the square root of x squared plus 1. And then, finally, if x is equal to tan theta, then that means theta is equal to the inverse tan of x. And so when we see that theta here, that theta there, we have to turn it into the inverse tan of x. So then this becomes inverse tan x. Sine theta was x over the square root of x squared plus 1. And cosine theta was 1 over the square root of x squared plus 1. So putting these together, we get inverse tan x plus x over x squared plus 1. So that one took almost as long as the other three combined, I think. Anyway, it looks like we do finally have some kind of an answer here. We put all this together. Running out of room to put all this stuff here. I'll come down here and just do final answer. The final answer, the first part of it, we got, what did we get? ln, or 1/2 ln x squared plus 1. 1/2 ln x squared plus 1. For the second part, we got 2 arctan x plus 2 inverse tan x. The third part, we got that minus 1 over 2 x squared plus 1. Sorry, 1 over 2 x squared plus 1. And then the last part, we got, let's see, that was plus, yeah, it was minus all that, right? I'm coming back up here and just looking that there's actually a minus sign right there. So that those have to be subtracted. So we're going to get minus inverse tan x, and then minus x over x squared plus 1. So notice in the end here, we actually do have a couple of like terms. So really, it's the very last step. We want to combine those. So 1/2 ln x squared plus 1. 2 arctan minus another arctan. We're just going to have 1 arctan left. So 1 inverse tangent there, and then minus 1 over 2 x squared plus 1, and then minus x over x squared plus 1. And now we have a couple of problems that I'd like you to try. On problem 1, it's a cubic again, and that one actually does have the repeated linear factor situation. So Try to remember what happens there. And then problem 3, if you notice, uh, problem 3, notice it is improper. Why is it improper? Well, if you look at the power in the numerator, x to the 5th. Power in the denominator, x to the 3rd. Right? So highest power is in the numerator. That's improper. That's the definition of an improper fraction. How do you deal with an improper fraction? What is the first thing you want to do? And that's the only time, in fact, that we're using step 1. If you look on the other side there, step 1 says divide if improper. Okay. Well, divide. How do you divide a fraction by another, or polynomial by another polynomial? Got to use long division. So I'm going to just try to see how many of you remember how to do long division now. That's what you have to do first on there. So divide x to the 3rd plus 1 into x to the 5th, x minus 1. If you can remember how to do it, do that. If you can't remember how to do it, just hold on and I'll show you how to do it in a little bit here. Problem 3 is also a difficult one. We'll go through that one at the end. If you want to try to figure it out by using the hint there, by all means do that too. So I'll give you guys about 10 minutes again to at least try to do some of these, maybe at least try to get through problem 1 and maybe try to do the long division on the other one. All right, so yeah, I'll be right back. I'll be back in about 10 minutes. If you have questions, Michael's here to answer them. So notice what he did on the one with the repeated linear factor. Two unknowns there, right? Oh, you're adding constants to all of them, it looks like there. Let's see.
On which part? On the top?
Like plus C1, plus C2, and stuff like that.
Oh, yeah.
Yeah, so you could just put the constant at the end. You don't need to worry about individual constants there, but yeah, for the most part, yeah. Everybody see how that works? And then for, yeah, that problem 2 actually ended up being easier than it probably should have been. Once you do the partial fraction decomposition, if you notice what happened there, it turned out that this factor that you got after doing the long division is the same as that one, right? And so those actually just ended up canceling each other out. And so what you ended up getting out of the end of that was just a nice, easy x squared and then 1 over x plus 1. So it actually ended up being easier than I thought it was going to be.
Yeah, I was expecting this on that myself.
Yeah, all that basically means is that x to the 3rd plus 1 actually is a factor of the, or I'm sorry, that has a factor that is the same as the factor that was in the numerator there. The x squared minus x plus 1 happened to be a factor of the x to the 5th plus x plus minus 1. And then the last problem, yeah, so what you're, let me see, what are you doing there?
I made the whole numerator u. That was a sub I chose.
Yeah, that's a good choice. But then in between between this step here and this step here.
Okay, yeah, I forgot to make a notation. What I did there was I used form 19 out of the cheat sheet that you have in the next section.
Yep, that's what I thought you did. Yeah, in fact, if everybody wants to turn over the to the next section, 7.5, and this is fine if you want to do this. I'm okay with it since you can use this on the test. You can use this table of integration formulas on the test. In fact, I'll include it with the test. If you look at form 19, number 19 on that, that's the one that Michael's using for what I was just circling right there. This integral right here is number 19. This thing is pathetic. Number 19. Yeah. Number 19 on that list. And so A in that case was just 1, and so he's just plugging it into that formula right there. Although it could have been done by partial fractions. In fact, that's the whole point of this problem, is that you would do that by partial fractions. But it's okay. You can use the form as well.